The first talk is by Dr. Hayim Shaul. He is a researcher at IBM Haifa Research Labs. Dr. Shaul completed his PhD in computational geometry under the supervision of Professor Misha Sharir at Tel Aviv University. After that, he was the co-founder and CTO of Divi Networks, a company founded by the IFC dealing with network optimizations. After that, he joined MIT as a research fellow in the CCL lab doing research in homomorphic encryption. Today, he is a researcher at IBM Research, continuing his research in secure multi-party computation. Today, Dr. Shaw will be talking about circuit optimizations and scheduling strategies with respect to fully homomorphic encryption.
Thank you all for joining me. My name is Hayim Shaul. I'm from IBM Research. In this talk, I'm going to talk about circuit optimizations and scheduling and caching strategies in the context of FHE. I'm going to show how it is easily done with Circ layers, which is a part of a bigger end-to-end platform called HE layers. And we're also going to see a practical example of how we improve the running time of a neural network, AlexNet, by 11%. If there is only one thing that you're going to take away from this talk, then let this be it. If you want to design a new circuit optimizer or a new scheduler or a new caching strategy, then I really think you should use Circ layer, which will let you focus on your code and on your research and not on the everything around it. So what are we going to do today? First, we're going to mention in a nutshell what is FHE. Then we're going to mention what is HE layers and how Circ layer fits into HE layers. We're going to give some intuition of how circuit optimizations work, and we're going to give some intuition of how circuit scheduling work and how they improve the running time of circuits. Then we're going to see a practical example. So what is FHE? FHE is an encryption scheme where we can encrypt and decrypt a message into ciphertext and decrypted ciphertext into a message. And we are also equipped with two functions, add and multiply, where both functions get two ciphertext and they output a ciphertext whose message that is encrypted inside the ciphertext is the sum or product of the two input ciphertext. So you can see that any polynomial can be computed with FHE over encrypted input, and any polynomial can be realized by an arithmetic circuit and actually by many different arithmetic circuits. And we already also know that any algorithm can be expressed as a polynomial. So it is really tempting to think or to try to develop a compiler that takes an algorithm and outputs a circuit or a polynomial that realizes it well. So there are some compilers that convert C++ code into FHE circuits, but the question of building such a compiler is not a new one, and actually it was studied in the past in the context of hardware circuits, where people have tried to take C++ or any code, any software code, and compile it into a hardware circuit. And it turns out that this doesn't work very well. And the reason that it doesn't work very well is because the underlying computation model is different in software and hardware. So to see why this is so, think of a sorting algorithm. So in software and comparison model, we can think of the algorithm as one that traverses a search tree, where all the possible permutations are the leaves of that search tree. And in every step we take, we perform some comparison. We compare two values, and the result of that comparison helps us eliminate at least half of the possible permutations. And since there are n factorial possible permutations, n is the size of the input, there are n factorial permutations, which are the leaves, and so the height of that tree is at least n log n, which is also how you prove that there is a lower bound for sorting of n log n. If you try to take this algorithm, such a sorting algorithm as is, and produce a circuit out of it, then you are going to end up visiting every node of the tree, and so the circuit is going to be of size n factorial. But this is, of course, not the best way to compute, to sort an array in hardware, in a circuit. There are better algorithms, for example, batcher sorting algorithm or Bitonic searching algorithm, where we have a sorting network that uses only n log square n um, gates. So it seems that at least for the near future, we will still need to code write code that fits FHE or circuit model, and we will not be able to compile algorithms written for comparison model and compile them into a circuit model. And there are some end-to-end platforms that help developers do that. Developers can write code in Python, and it will be converted into C++, and the C++ code will be converted into a circuit, and the developer can intervene at every step and change the code that the compiler generated, or write its own his or her own code. And this is exactly what HE Layers is. So HE Layers is such a platform. It has layers from the bottommost, which is the FHE schemes, to the topmost, which is the Python and the application layer. And what actually happens when you write code in such a platform, either in Python or in C++, eventually it is transformed into an assembly code, which is then executed on the CPU. So where does Circ layer fit in this model? So it's here. So it's the assembly code. So instead of compiling the code into an assembly code and then executing it on a CPU, we transform the code. We compile the code into something that is a little bit a higher level than assembly code. It has some higher level description, and in runtime, that is going to be uh, executed on the CPU. This is very much like Java's just-in-time compiler or Java virtual machine, which keeps the code in something lower than Java, but higher than assembly, and only when in running time um, actually transform the code into something executable. So what are the different components of Circ layer? We have the circuit, the optimizer, and the scheduler. The circuit is a graph representation of the code. The optimizer is a tool that modifies a circuit to an equivalent circuit that hopefully performs better. The scheduler is a module that decides on the order of execution of the gates. The scheduler can also decide on how and when ciphertexts are going to be cached to the disk or prefetched from the disk. Both the optimizer and the scheduler are strategy classes, and they are easy to replace. They are easy to be, it's easy to write your own optimizer and scheduler and use them to optimize and to schedule a circuit. So let's see what the circuit is. Um, so obviously, FHE circuit does not contain any branches. Any circuit doesn't contain any branches. In FHE, that is inherent from the encryption scheme. Any comparison, had it been possible, would have leaked some information about the data. So there are no branches. The circuit itself is a directed acyclic graph where nodes, also called gates, are the operations, add, addition, multiplication, etc. And the edges are the ciphertext. So how do we extract the circuit from an FHE code? So FHE is input oblivious. That means that for any input, the same gates are going to be executed. So we use that and run the circuit, the given circuit, the code on some arbitrary input, and we record the gates that are executed as they execute and use that log to construct the circuit eventually. So the optimizer module. Um, so the optimizer module takes a circuit that was generated in a previous step, and it changes it to an equivalent circuit, hopefully one that performs better. So how does it do that? So we're going to see a few examples of intuitions of how circuits can be improved. Um, so consider this example. Um, so we see here two circuits. Here the one on the left and the one on the right. They both compute the same polynomial. They realize the polynomial x1 times x2 times x3 times x4. But the circuit on the right is shallower, and that means that it is easier to parallelize. So, for example, this gate here can be computed at the same time with this gate. With FHE, there are other advantages to having a shallower circuit coming from the specifics of FHE, but in general, shallower uh, circuits are better also in hardware. For a second example, consider these two circuits. They both realize the same polynomial, x plus y squared, but as you can see, the circuit on the right is significantly smaller, it has less gates, and it is shallower. Uh, In 1973, Peterson and Stockmeyer gave a recipe of how to construct a circuit realizing a polynomial, which is better than the naive circuit. They did that in the context of polynomials over matrices. In 2017, CKKS, Chong, Kim, and Song used Peterson-Stockmeyer in the context of FHE. Still, Peterson-Stockmeyer gave the recipe for univariate polynomials. If you extend the recipe to multivariate polynomials, things deteriorate exponentially with the number of variables. So the recipe of Peterson-Stockmeyer is just a heuristic that gives us something better than the naive solution, but still it is not the optimal circuit that realizes the polynomial. Finding the optimal circuit that realizes the polynomial is a NP-hard question, and it turns out that it is NP-hard even for simple polynomials such as x to the power of n. Finally, I want to mention that there are FHE-specific optimizations, such as where to place the bootstrapping gates and where to place the rescaling gates, and moving them around the circuit can also improve the performance of the circuit. So reviewing what is currently known in the field, there are quite a few circuit optimizers out there. For example, EVA, Chingulata, ngraph, and more. All these circuit optimizers are a part of a system, and you cannot uh, change the optimizer, or you cannot write your own optimizer and change it and easily run your version of optimizer within the system that they come inside. Uh, so again, in our framework in Circler, the optimizer is just a strategy class, and you can replace it with your own. You can change it. We have several versions of optimizers. The next module in Circler is the scheduler. So after the circuit has been optimized and been fixed, the scheduler is the module that is responsible of determining which gates are executed when. And apparently the order in which gates are executed matters. So let's see. So let's see how the scheduling can affect the performance of a circuit. So remember that the scheduler runs, the module kicks in after the optimizer has optimized the circuit, and the scheduler gets a fixed circuit that it needs to determine how to execute. So consider, for example, this circuit. So it has two parts. One part that computes a function of x and y, and one part that computes z to the power of 16 with a sequence of 4 multiplication gates. And suppose that you want to execute a circuit with more than one CPU. Let's say you have two or more CPUs, then obviously the critical path of this circuit is these 4 multiplication gates. And even if you assign both CPUs to first compute this part of the circuit, then you're going to end up having to compute this critical path, in which case the two CPUs will not be able to work in parallel over the critical path. Only one CPU will work, and the other CPU will stay idle. So it makes more sense. It will be more efficient to start executing this critical path sooner with one CPU and having the other CPU executing this part of the circuit. The next example shows a strategy that we call rush ahead. This strategy follows the execution order of the C++ code that generated this circuit, but with the exception that if a gate, if there is an idle CPU and there is a gate that is ready to be executed, then we can rush ahead and go ahead and execute it, even if the C++ code would not have done that if it were running. To see why this is better, so see, for example, this circuit. It's a circuit of a neural network, and you can actually see the different layers. So each layer is like a cluster of a lot of gates, and in between the layers, you have some strings of gates. And usually, when people write C++ code, they write it in a loop where they execute one layer, and after a layer has finished executing, then they move on to the next layer. So with the rush ahead strategy, you don't have to wait for a layer to finish. Once, if there are idle CPUs and there are gates on the next layer that are ready to be executed, then the circuit, the scheduler, can go ahead and start executing them. The next strategy is what we call in-place computation. Um, so think, for example, we have a C++ code where we assign x times y into a variable called temp. What actually happens is x is copied into temp, and then temp and y are multiplied. So if x, for example, is not going to be used later in the computation, we can just multiply y into x and rename the variable, so x will now be called temp. But for example here, what we have here is x is used twice, once for this gate and one for this gate. So we cannot perform the in-place computation. But if we defer one of these gates, for example, if we defer this gate to be executed after this gate has been executed, then we can compute the multiplication, this multiplication gate in place, meaning that we can destroy x and multiply y onto it. As another example, we see that once all the gates that need ciphertext has been executed, then we can remove the ciphertext from memory. So we can, or the scheduler, one of the strategies is to rearrange the gates such that the footprint, the RAM footprint, will be as small as possible, meaning that we will free as many ciphertext as early as possible as we can. Uh, uh, a similar strategy or a similar functionality is caching. The scheduler, since it knows when each gate is going to be executed and which ciphertext each gate needs, the scheduler can cache, can write ciphertext into the disk and prefetch them just before they are needed for the execution of a gate. So this caching and prefetching can also decrease the RAM footprint of running a circuit without degrading the running time. The state of the art is Mage that was presented in Usenix last year. They showed a system that as a pre-processing step executes a circuit and records the access pattern to the memory, where and when each ciphertext was accessed. And in consequent runs, they cache ciphertext to the disk when they see that they are not going to be accessed in the near future, and they prefetch the ciphertext from the disk just before they are used by by the circuit. So therefore, they don't see any any running time degradation, while they can execute circuits with much smaller RAM footprint. So in our framework, the scheduler is a strategy class and can be replaced. We have several versions of schedulers, and you can also write your own strategy class to try your own scheduler, your own caching and prefetching strategies. So next I'm going to show an example of how we run AlexNet and obtained better running times. So we chose AlexNet because this is the largest neural network that we don't need bootstrapping or client aid to run it. So the state of the art runs the AlexNet in 648 seconds. Uh, this was done in a paper by a team from IBM, and they used HE layers to achieve a better packing for the input for the ciphertext. With CircLayer, with using the rush ahead heuristic, we reduced the running time to 605 seconds. That's an improvement of 7%. And using rush ahead and preferring in place computation, we reduced the running time further to 580 seconds, which is an improvement of 11%. So next I want to show you a little code just to demonstrate how easy it is to use CircLayer. We're going to see a code that extracts an underlying circuit from an FHE code, and then we're going to see a code run that circuit. The CircLayer again is a part of the HLayers package that you can download from the internet. First, let's see an example of how to extract a circuit. Um, so in HE layers, each ciphertext have a context. It can be a CIL, CKKS context, or a BGV, HLE BGV context, for example. And we have one more context, which is the circuit context. And it is very easy to change the context for for an existing FHE code. So this is what we see here in the code. The first few lines just initialize the context of the circuit, which is the context that logs the operations that are done on the ciphertext. Then we do some neural network initialization. We initialize the neural network. Then we have some code that takes the input to the neural network and encrypts it. And then we run the forward pass of the network on the given input, and the output is some ciphertext which we then get from the network. So we label the input as input and we label the output as output, and that is it. So after we run the forward pass, what we have in the circuit context is a construct of a circuit that we can either write to the disk or later run it using the runner. So the next code is doing exactly that. It takes a circuit construction constructed in the previous step and run it. So here to add that between the previous step we started the circuit and this, we can perform circuit optimization on the construction that we have, either in memory or we can write the circuit description to the disk, to a file, and operate on that file with some external tools, and then reread the file and construct the circuit again, the new optimized circuit in memory. So once we have done that, once we have a circuit construction in memory, either optimized or not optimized, um, we want to execute it, we want to run it. To do that, we need a memory bank, a cache of ciphertext that we need uh, to, uh, to initialize and to encrypt, uh, to fill it with ciphertext. This is exactly what is done here. We clear memory cache and encrypt a cipher, encrypt cipher, encrypt input the circuit, and we insert the ciphertext into the memory bank in the cache. We declare the runner, so the runner gets as parameters the circuit it's going to execute in circuit and the strategy that it is going to use for the schedule. So here you can choose strategy to be a strategy that fits your specific needs, your specific goals, or your specific circuit. If you know that your circuit works better with a different strategy, then you can change the strategy here. So next we just call the run function, just runs the circuit using the inputs and using the strategy that were given in the initialization. Um, so next, after we have run the circuit, we can extract the output, which is labeled by output, by the label output. So choosing a different strategy involves initializing the runner with a different strategy. Um, you can use a different strategy that we supply, or you can write your own strategy. For example, if you have a different goal, or if you know that your circuit will run better with some strategy that uh, that you can better design, then you can write your own strategy and give it here as an argument to initialize the runner. A strategy that you write can also execute Python code, an external Python code, or some cloud service that solves uh, some optimization problem. For example, the simplex algorithm. All that can be packed into a strategy and be given to the runner to use. So to write a strategy, you need to implement these four functions, initialization, obviously, and three functions done, determining whether the execution of the circuit is done, get next node to execute, which gives the runner the next node that it needs to execute, and done executing is a signal that the runner signals the strategy that the execution of a gate has been completed. So to conclude, we've seen that CircLayer extends HE layers to add circuit optimization and scheduling strategies. I think that researchers who want to research new heuristics for circuit optimization or for scheduling strategies, it is really easy, and they can benefit from using CircLayer, since CircLayer is an end-to-end platform that takes all the way from Python code or C++ code all the way to actually running the code on one or more CPUs and giving them the advantage of changing the optimization or the scheduling strategy where they write only the strategy that they want to check. We've also seen that using simple scheduling strategies can improve the running time of AlexNet, of a neural network, uh, improving the state of the art by more than 10%. Thank you.
Thanks. I think Hayim is joined in the call. I'll open the floor for any questions. Hayim, can you hear me? Are you able
Yes,
to? Oh,
I can
great.
hear
Yeah.
you.
Yeah. Thanks very much. Yeah, that was a very interesting talk. Yeah. Are there any questions? Please feel free to post it on the chat. If or else we can even promote you to panelists if you want to ask it verbally. So please feel free to go ahead. I can start off. So the HE layers, I think maybe you can probably just give a brief overview of how it's available in open source. I understand there's a Docker image available for public usage. Is CircLayers part of the Docker image, or will it be made part of that very soon?
Yes, it will be made part of the HLayers package, hopefully in the next release. Yeah.
That's good. And so currently, is there? But so the is the capabilities for like what are the capabilities that will be expected in the public doc image from the CircLayers perspective? Are all the features you described going to be in there, or is there some subset which is initially going to be implemented and then you kind of add things as they go along?
Yeah, we're going to start with something more minimal, and then we're going to add more functionality as we go along. So obviously there is going to be the functionality to log a circuit and write it into the disk, into a file. Yeah, so some scheduling strategies are also going to be there, and yeah, so that's what we're going to start with, and we're going to add more strategies for scheduling and more optimizing scheduling strategies as we go along. Yes.
Right. Okay. Are there any other questions? Also, please feel free to raise your hand, anyone in the audience, if you wish to ask a question. I can even promote you and allow you to ask. Even that works. Yeah, I see Pradeep has a question. Thanks, Hayim. Great talk. Regarding the 11% improvement over the state of the art, is there a theoretical bound analysis that shows the absolute limit of improvement that could be achieved?
I don't know. I don't think we definitely don't have any theoretical bounds of how much improvement you can achieve. I think this is very circuit dependent. Yeah, I really don't have any. Yeah, so maybe for specific circuits we can find bounds, but definitely it's not something generic that we can think of now.
Right. And just to follow, how network dependent is this? Like, for example, would you see a similar 11% for say ResNet, or even maybe completely different architectures, like say just being like say if you have a logistic regression or non deep neural networks, would you expect to see similar lower or higher improvements?
That's a good question. So basically, the improvement comes from two factors. One factor was that we rushed ahead, and so then obviously the improvement depends on how well you implemented your code. So it's not always easy to write C++ code that parallelizes easily. And if you don't keep parallelization in mind, then it sometimes is hard to achieve, especially, for example, in convolution networks, because there the yeah, I think in convolution in convolution layers, it's harder to write a function a loop that is easy to parallelize. So the other factor for getting improvements is the using the in place, computing things in place. That means avoiding copying unnecessarily data, unnecessarily ciphertext. And again, this is very dependent on how well you write your code using moving, but also rearranging your code in such a way that you will not need to copy ciphertext. Again, this is not always easy to write, but this is something that is automatically achieved with CircLayer. The scheduler just so when in-place computation is possible, it just perform the computation in place, and sometimes it even defers some computation to be able to perform the next computation in place. That's to save a copy. So again, a convolution layer, I think was more challenging to write in C++. So the improvement was bigger there in convolution layers. I guess convolution is more complicated than fully connected, because it's like fully connected is just multiplication by a matrix, and convolution layer is like more complicated, where you have a kernel, a small kernel, and you place it in every location on the input. Yeah, I hope that answered the question.
Sure, yeah. But have you, so it is definitely, you would say that something like linear logistic regression might actually be more straightforward.
Yes, I think that's an easier task, an easier computation task.
Fair enough. Yeah. Pradeep, do you have any follow-up questions?
No, that was yeah. I got connected for a little while and moving from this analyst. I guess I missed, but I think I heard most of Hayim's response. Yeah, no, I think I understand. Thanks.
Yeah.
Very good talk. Yeah.
Thank you.
Thank you. Any other questions? Yeah, maybe I can ask a final one. So, uh, how where do you see the scope of this in? I mean, obviously, going to more complex neural networks, say like recurrent nets and LSTMs and the other kind of structures are going to be way more complicated in FHE, because inherently nonlinear operations, non-polynomial operations are difficult. But can circ layers do something about that? Is there any way to optimize, say, some nonlinear operations or polynomial approximations for any of these nonlinear optimizations, nonlinear structures? Sorry.
Yes. So obviously, I think that using a circuit. So okay, starting with with the rush ahead, then you cannot do worse than the C++ code, because you're just following the same execution order as the C++ code. You can only be better because you can rush ahead and use idle CPUs that the C++ code did not use. Also, again, it is easier to find in place to optimize the in place what can be in place computation. But the more interesting question is whether you can take the circuit and replace it with a different circuit, very much like what Peterson-Stockmeyer's did back in '73, and also CKKS used in 2017, where they had a polynomial where they wanted to compute a polynomial, but just writing the naive circuit was significantly more expensive than using the Peterson-Stockmeyer scheme. But that is not the optimal thing to do. There are so in general, this is an NP-hard question. So we don't have a good generic solution to every polynomial. And it turns out that even for simple polynomials, even for x to the power of n, the question is NP-hard. So the gap between between what we know and what is between the lower bound and the upper bounds that we have is not very big for n to the power of n. It's yeah, so it's not very big. It's really small, but still we don't know how to achieve. We don't know how to bridge the gap. We don't know what is the true value, the true size of the circuit that computes to x to the power of n. So for even more complicated polynomials, then we are really in the dark. We have no idea. So we have heuristics, but definitely not something that works optimally well for all polynomials.
Okay, that's good. I see Apurva has a question. What's the overhead of each component of Circlair?
Okay, so let's just go over them. So the first component is the one that records the gates. It's in this component runs in plain text, so the overhead is very minimal. The next component, the optimizer. So that is that can be hard. I mean, and you might be forced to have the optimizer might be a heavy component. The scheduler is not very heavy. I'm tempted to say that it is not very heavy. So executing the gates, you still execute the same gates. It depends on how much computation you need to invest in your scheduler to find the next gate to execute. So for what we have used, that execution was finding the next gate to execute was not very time consuming, because we had everything in heaps and in data structures that allowed us to find the next gate to execute. But generally speaking, if your scheduler needs a more complicated reasoning, more complicated computation to do, then that might be also time consuming. But keep in mind that you are comparing that to the actual computation of FHE gates, which are also time consuming.
Thanks. Apurva, do you have anything else to follow up?
Sorry, what?
I was just asking Apurva if she has any follow-up.
I guess I wanted to also ask about like the scheduler overhead. Can you hear me?
Yeah, we can hear you.
Yes. So what was the question?
Hello?
Yes. Yeah, we can hear you. We can hear you.
Oh, okay. Yeah, I was just asking a follow-up on like, have you looked at using a more using a more heavy-weighted scheduler for better improvements in like better performance improvements?
No, so we are currently trying to use the simplex heuristic to find a better, or to see what's the difference between using a simplex and then how will the simplex method will compare to just using the natural scheduling, which is like doing whatever C++ had made and rushing ahead and in place. So then the using the simplex is heavy, and it is so we don't have any final results about that I can share, but yeah, this is something that we have been thinking about.
Cool, thanks. I just had one final question. So there is also a Python wrapper around itchy layers, itchy layers. So would
Thanks for answering.
oh, okay. And does Circulars work on that as well?
Yeah, so Circular is actually a layer, yeah, so it's a layer that is below the entire HE layers. So after you have written your Python or C++ code and you have debugged it and everything works and you want to execute the FHE code, then instead of just compiling into executable and running it, you can, or in our vision, you will compile it into a circuit and then have a runner read that circuit description and execute it on your CPU or multiple CPUs.
Right. Oh, excellent. Okay, that's good to know. All right. I don't see any further questions. Yeah, we can virtually thank the speaker, Dr. Shaul. Thank you very much. It was very enlightening.
Thank you for having me. Great question,
No problem.
by the way.
Thank you.